discovered that the laws of physics which govern the motion and behavior of large bodies was not adequate to account for the motion of tiny particles such as atoms and electrons. With his model, Bohr could explain the behavior of atoms with one electron. But he could not predict the radiation spectrum observed for other, more complex atoms. The seeds of a new model would come from the concept that all forms of electromagnetic radiation exhibit the properties of waves and particles. This concept led the aristocratic French naval officer Louis de Broglie to speculate that particles of matter might also exhibit wave characteristics, although these waves would not be obvious at the scale of day-to-day observation. Even in the bathtub, we can see two waves interact to produce a larger wave, then pass right through each other without injuring each other. Imagine two particles, like a baseball and a bat, somehow becoming one, then passing right through each other. And yet, experiments with particles as small as electrons show they produce patterns we can only explain with waves. The pattern can be produced even if only one electron at a time passes through the slits. De Broglie suggested that his matter waves would have a wavelength inversely proportional to the electron's momentum, which could be calculated by multiplying the mass of the electron by its velocity. De Broglie showed that by using his matter waves, he could predict each allowable orbit and its radius for the hydrogen atom. He also came up with the same energy levels as those predicted by the Bohr model. De Broglie proposed that in the ground state, or first energy level, the circumference of the electron orbit is one de Broglie wavelength. This single wavelength fits around the atom's nucleus at a distance that allows the wave to interfere with itself and form a stationary or standing matter wave. In the second orbit, n equals 2, two de Broglie wavelengths fit about the nucleus, at a distance which once again produces a standing matter wave. This wave mechanical concept resulted in a new vision of the atom, which replaced Bohr's. It was Austrian physicist Erwin Schrödinger who first visualized the concept. He proposed an atom with a positively charged nucleus surrounded by a spherical cloud of electron waves. Werner Heisenberg, working with Max Born in Germany, arrived at the same model of the hydrogen atom as Schrödinger, but on the basis of different physical assumptions and using different mathematics. The wave mechanical model of the atom implies that the path taken by an electron cannot be predicted, and that the position of an electron at a particular instant can only be stated as a probability. The most dense part of the cloud is where the probability of locating an electron is greatest. We can look at this uncertainty about electron position and velocity in another way. In our macroscopic world, photons of light colliding with a relatively large mass do not measurably affect its position or rate of motion. But photons striking an object as tiny as an electron will have an effect. The means used to determine the position of the electron, light, is close to the scale of an electron. As a result, the collision between photon and electron can alter the electron's velocity. Conversely, methods of measuring electron velocity make its position uncertain. Heisenberg's uncertainty principle explains why the position and momentum of an electron in motion cannot be measured simultaneously with great precision. In other words, there is a natural limit to the accuracy of certain kinds of measurements. Mathematically, the uncertainty principle is this: the uncertainty in position times the uncertainty in momentum equals Planck's constant. As the uncertainty about one shrinks, the uncertainty about the other has to grow to keep the equation balanced. The wave mechanical model further extended the concept of the quantum. Originally, it had been used to describe bundles of radiation that could only have certain discrete permissible energy levels. Bohr extended the quantum concept to discrete permissible orbits, to which he assigned quantum numbers for reference, generally described by the letter n. The wave mechanical model defined the discrete permissible shapes of orbit clouds using a quantum number L. The orientation of that shape in space using quantum number m, and possible spins on the electron described by quantum number s. For a hydrogen atom with orbit n equals 1, there is only one possible shape. This shape has the quantum number L equal to 0. Since the shape is spherical, it can have only one orientation in space, described by the quantum number m equals 0. Hydrogen with only one electron can only ever have one spin, s equals 1/2, so we will ignore it after this example. When n equals 2, two shapes are possible. L equals 0 and L equals 1. This second shape can have several orientations in space, m equals 1, m equals 0, and m equals -1. Using this simple set of quantum numbers, an ever more complex set of energy states can be described, not only for the hydrogen atom. But at last, a method had been found for describing the more complex energy states of multi-electron atoms, and also for multi-atom compounds. This wave mechanical model has remained the accepted model of the atom since its introduction in the mid-20s. History does not record who first asked the question, how big is small? The list of those who contributed answers, however, stretches forward from its beginnings over 2,000 years ago. It is the nature of science never to close the books on any field of inquiry worthy of investigation. The next chapter of the structure of the atom is waiting to be written.